So in today's class, we are going to see a few more techniques for image segmentation, and these techniques are mainly the one listed here. So we'll see mainly region growing techniques, region split and merge, and then a technique based on watershed. Let us quickly have the recap of what we did in the last class, and then we'll go for the new techniques. Mainly what I have colored here in blue, this already we have seen in the last class, and these are the mainly techniques that we are going to discuss today. So in the last class we saw what we mean by segmentation. So this is when we talk about segmenting an image, this is actually the task of dividing the image into some segments, right? And when we group some pixels and say that this is one segment, then that means that all the pixels that are belonging to a particular segment, they will share the common characteristics, and such segment are called the homogeneous segment, because all the pixels will be homogeneous. They will have the same characteristics. Okay? And when we are doing actually the image segmentation, or when we divide the image into segments, this process actually provides us a more meaningful representation of the image, because once we divide the image into various segments, then there are a lot of tasks that can be actually performed based on this information. Okay. So this process of segmentation actually provides us more meaningful image, and whatever is the outcome of this process, that actually makes easier to analyze that image. As we discussed in the last class, that if suppose this is the image given, and then if we segment this image into multiple segments, and then by analyzing those segments, we can tell which part is bird, or which part is trunk, or which part is background, and so on. Okay, so a lot of details and a lot of tasks can be performed based on the segmentation outcome. We have discussed this threshold-based segmentation in the last class, and this technique was only applicable when the image had the grayscale distributions, where if you plot its histogram, the histogram has peaks, multiple. I mean, you can divide the histogram into some peaks, and if image is not of that nature, then we cannot make use of the thresholding-based image segmentation. So, for example, in this image, you see that there are some portions in the image which are white, and there are some portions in the image which are black or dark. So when we plot its histogram, we get a histogram like this, where we have in histogram we have two peaks, one here and another here. So in this scenario, we can have we can put a threshold on the intensity, and then say that anything which is below this intensity is one segment, and anything which is above this intensity is another segment. So this is this technique is applicable only in very specific cases. And how will you find out whether this is applicable or not? So for that, you have to plot its histogram, and then you have to analyze its histogram. Threshold can be applied. Based on how you are applying the threshold on the image, the technique can be divided into three types: global thresholding, where same threshold is used on the entire image; adaptive thresholding, where threshold is actually decided based on the locations. Maybe so in your image, the threshold which is being used here may not be used at another place. Right? If that is the case, then that's adaptive thresholding, and in some cases this is very useful. And we also saw how to compute the threshold, which is optimal, and by considering optimal, global, and adaptive thresholding, how to compute the optimal threshold, right? If we apply this process and get the optimal threshold, then you can say this is the kind of third way of doing the thresholding-based segmentation. And what was the optimality criteria that we used there? It was based on the minimum average segmentation error. Okay. So this all we have discussed in the last class in detail. Now let us discuss the new techniques. So the first few techniques that we are going to discuss here, they are based on region. Till now we have done threshold-based techniques. Now we are talking about region-based segmentation techniques, and then at the end, briefly we'll talk about edge-based segmentation techniques. So when we are talking about region-based segmentation technique here, our objective is to find out the region in the image which have the common characteristics, and then label them like this, as you see in the image on the right. So all the pixels which have the common characteristic, they are just given one label. As you see, all the pixels here which are representing the grass, you can say that they have the common characteristic, so they are represented by a common label here in the output. Similarly, all the pixels which are, let's say, in this wall part, they have been given a common label. Similarly, this region is little brighter, so they have been given a different label, and so on. So in the region-based segmentation, we have to find out the regions which are where the pixels have the common characteristics. So in summary, in the region-based segmentation, all the techniques that we are going to see here, we have to analyze the pixels, and then we have to group the pixels which are having the common characteristics. Okay. Now, when we are discussing these segmentation techniques, we are going to follow some notations. So here, let us say R represents our entire image region. So whatever image we are going to segment, that is represented by R. Like for example, here this entire thing is an R, is the region R. Now, if let's say this image is segmented into some segments, so those segments we can say that they are R1, R2, R3, and so on. So for example, this is R1. Similarly, this is R2. Okay, and if let's say this is segmented like this, so this is R3, and this is R4, and so on. Okay, so segmentation is nothing but the process of segmentation. It can be viewed as a process that partitions R, the entire image region, into sub-regions R1, R2, R3, and so on till Rn, you can say. So if let's say the image R is being partitioned into these segments, then we will see that if you take the union of these segments or these regions R1, R2, R3, they will actually satisfy few characteristics or few properties. Those properties are listed here. So if you take the union of all the segments that we have got from R, if you take the union of R, it's obvious that we'll get the complete R back. If you take the union of R, Ri's, then we will get back the complete R. As you can see here, if you take the union of R1, R2, R3, R4, then we are going to get back original image. Okay, and it says that if you are saying that all the pixels, let's say here, are belonging to region R3, that means all the pixels there, they are connected to each other. If in Ri, it is a connected region. Right? All pixels are connected, and we have already discussed at the beginning of this course what we mean by connectedness. Right? So there we have to check the property of neighborhood property, and then also some gray label property, and based on that we can say that the two pixels whether they are connected or they are not connected. Right? So this already we have discussed. So in any region, we'll see that all the pixels will be connected, and in a broader way we can say that the pixels will be connected if they have share the common characteristics. If you take the intersection of any two regions Ri and Rj, let's say, it should be phi. It's also obvious because if there is any common characteristic between an R1, Ri and Rj, then they would have not been the separate segment, they would have been the same segment. So that is why if you take the intersection of R1 and R2 or Ri and Rj, you will not find anything in common, right? As you can see here, if you take the intersection of R1 and R3 or R1 and R2, there is nothing in common. Okay, and the fourth property, it says that P of Ri will be true. So P basically defines a logical predicate, and Ri is the input to it. So it says that the pixels that are following that are falling in region Ri, they will actually have some common property. Okay. So this common characteristics we are going to see. This may be because of color, or maybe gray level, or maybe texture. But all the pixels which are falling in one region, they will, as we said, that in any segment the pixels are going to be homogeneous, so they will have the same characteristics. And similarly, next fifth property, if you just take the union of Ri and Rj, and then you analyze that property, that predicate, you will find that it will be false. This is going to be true when all the pixels are going to have the same property. Like we said that P of Ri is true because in Ri all the pixels are having the same property. But if we take the union of Ri and Rj, Ri has one kind of property, Rj has different kind of property. So if you take the union, you will find that the region that you are going to get after computing Ri and Rj, it will have two types of pixels, right? One which are coming from R1, Ri, and another which are coming from Rj, right? So since you have two kinds of pixels in this union, so then if you calculate the properties, you will not find that all pixels having the same property. They will have one of them, some of them will have one property, and some of them will have the different kind of properties, right? So that is why if you take the union of any two regions and then you analyze this property or this predicate, you will find that this will be false. Okay. So all the techniques that we are going to discuss here, they will be actually following all these properties. Mainly we are going to discuss these techniques here: region growing technique, unseeded region growing technique, and then region split and merge technique, and then a technique based on watersheds. And there's another technique also which falls in region based segmentation. It's called fast scanning, but we'll not see this in detail. Okay, so let us discuss the region growing technique. The concept is very simple here. So as the name suggests, it says it's a region growing. Right? So in this technique, when we want to segment any image into different segments, we start by choosing a particular pixel at some place in the image, and then we try to this pixel we try to group or associate other pixels in the image which are having similar kind of properties, right? You can understand this by considering this example. Suppose in this image our objective is to partition all the segments that are there. So let us say we start by considering this particular point here on this part, maybe let's say in the flower petal. So when you start from this point and then you analyze its neighbor, you will find that if you let's say I draw a 3x3 neighborhood for this pixel here. You find that all the pixels which are in the surrounding for this pixel which is I marked here, let's say this is the pixel here. For this pixel, all the pixels that are here in the surrounding, they all have the same kind of color, right? Let's say our common characteristic that we are analyzing is the color. So based on color, we can say that all the neighboring 8 pixels, they can be actually associated with this pixel, because they also have the same property. So that way we'll see that initially we had just one pixel, but now all these 8 pixels have joined, so our region has grown. We can say that initially our region was just one pixel. Now since other neighboring pixels are also having the similar characteristics, so by incorporating those pixels also in the group, we can say that the group of pixels the size has raised. And now in the group we have total 9 pixels. So initially we had only one pixel. Now it is a group of 9 pixels. Now again we can perform the same process on all these boundary pixels. 8 boundary pixels we have, and for all these 8 boundary pixels we analyze their neighbors, and if those neighbors are also sharing the similar characteristic that these pixels have, then again we will move this area. So let's say for all the 8 pixels, whatever the neighboring pixels we have, they also share the same characteristics, then this region will actually increase. So like that this process proceeds, and we keep doing till we keep enlarging this region as long as we find that the neighboring pixels are having the similar characteristic. As soon as we find that there is a pixel where the characteristic is different from the pixel that we have already grouped here, then we will stop there. So for example, in this case, we start from here, but as soon as we reach to the boundary of this petal, let us say somewhere here, then we stop. So that way you will find that we will get the shape of this petal like this, right? As you see the final outcome here in this last image. So in the first image here, we have started with a small region, maybe you can say that with 1 pixel, and then this region has grown, and then this has further grown, and at the end we get a final region like this. Okay. The starting pixel that we consider is called a seed point here, because that is the seed for the ultimate segment that we are going to get. So there are some key factors like how to select the seed point, and then what is the similarity criteria we are going to use. So if it is a grayscale image, then we can use based on, let's say, criteria based on gray level. If it is a gray level difference or gray level variance, if it is a color image, we can use color information, or we can also use the textural information. So based on what information we are using for computing the similarity, we can actually enlarge the area. Again, spatial proximity, when we are saying that we are going to analyze the neighbor, how we are going to compute the adjacency, which one, what neighbors are going to be called adjacent or what neighbors are not adjacent. So based on that, the region will grow. Now, what we mean by adjacency, how we compute it, we have already discussed in one of the class. So I hope you remember that. And then we need to also define in this case what is the stopping rule, where this region which is growing will stop, where this process of growing the region will stop. So that also need to be decided. As I just said here that let us say we are grouping the pixels based on the color. So as soon as you get a pixel of different color, then you will stop here. So for any similarity criteria that you are considering from here, for that actually you need to decide this stopping rule. Like for example, if you're let's say using the gray level variance, so variance is a quantity. So based on that, based on the threshold, you have to decide what should be the variance for which you should enlarge the region and what should be the variance for which you should stop. So all these are the key factors when we are using this region-based technique for segmentation. Again, this technique is applicable at few places. For example, let's say consider a scenario here where our objective is to actually segment, or our objective is to isolate the strongest lightning region in this particular image. Right? That means we want to actually segment this lightning part of the image. So in this case, we can choose a seed point, and you know that all the pixels which are part of this lightning, they are very bright. So if you choose, if you can choose any pixel on this lightning part, and then you grow your region, then you will get actually the final outcome. I mean, you will be able to actually segment this lightning part in the image. Now, depending upon what kind of what threshold you use, as I said, this is a stopping criteria here. So let's say you are grouping the pixels based on the intensity. So you will be using some intensity, some threshold that when you are analyzing two pixels, whether you will consider them similar or not. So let's say you are using a very strong threshold. If you are saying that anything which is 255 will be only considered similar. So in that case, you find that this is very thin kind of image that you get here. But if you relax your threshold, you say anything which is between 255 to 225 to 255 will be considered same. So then you get an image like this. Similarly, if you choose a different range, 190 to 225, then you get a different kind of output. Similarly, 155 to 255, you are getting a different kind of output. So depending upon what stopping rule you have used or what threshold you are putting on the intensity, depending upon that you can get the output. Now the question comes here: what should be the seed point? So as you know that in the lightning part, you will have a very bright pixel. So that, and since this is a grayscale image where the highest intensity is 255, so we can say that all the 255 values which you have in this area, they can serve as seed point. So in some sense, you can say that in the first image that what you see here, this is an image which is actually showing the seed points, all the possible seed points. Okay. There's another case where this kind of technique may be useful. This is the detection of weld failure. So, for example, you have two blocks of the material, and you have welded them, and now you try to find out whether they have got welded properly or not. So if they have got welded properly, then you will not see any. And if you let's say take the X-ray kind of image for that welded combined block, then if the two blocks have got joined together properly, then you will not find any space in between, and you will not find any break like this in the image. But if it is there, then these regions can be segmented with the help of this region-based segmentation, where again, as you see, these this failure, the pixels which are showing the failure, they are actually appearing bright. So we can consider 255 as in this image as the starting pixel or the seed pixel, and then by using some threshold criteria, we can grow the region and get these image, these portions segmented. So in ideal case, so suppose you want to detect the weld failure. So in the weld failure, what will be given to us as input? Input will be this welded block. Now we have to, let's say, get the X-ray kind of image from this, and then we have to analyze these segments. If it is properly welded, then you will see that this whole block will be just one segment. But if it is not properly welded, then you will see that it will not be only one block. You will see some small blocks like this, or small segments like this in the image. So by analyzing these segments, you can tell whether the welding has been done properly or not. If there is only one block, or the entire region is just one region, then it's a good welding. But if you get some some blocks or some segments inside the region, inside this image, then you can assume that this is not a properly welded block. Okay, so in this scenario also this can be useful. So what are the steps when we are going to use the region growing technique? So mainly we have two steps that we need to follow. One is to find out the starting point, that means to find out the seed pixel, and we can also say we need to also find out the similarity properties that based on which we are going to grow the region. So that we are going to define in the step 1, and once that is decided, then based on the technique that we discussed, or based on the neighborhood information, or based on the adjacency information, we have to grow the region starting from the seed point. Okay. One good thing with this technique is that we get a group of pixels which are having very good connectivity. Okay. This basically you can understand from the case that we had for the thresholding based technique. For example, here in this case, if we are applying the threshold, in this case we are not checking the connectedness of the pixels. When we are saying that the two pixels have the same kind of when we are saying that the two pixels belong to the same segment, we are not bothered whether they are adjacent to each other or not. For example, here we have two segments, foreground and background. Now when we are saying that this particular pixel and this particular pixel, they belong to the same segment, at that time we are not checking whether they are really connected or not, because in the process of segmentation we also want a connected region. But in this particular case, when two pixels are put in the same group, they may be connected and they may not be connected, right? But in this particular case here, when we are using the region growing technique, we'll see that whatever output we are getting, there we will have very good connectivity, because this whole process is based on the connectivity. Okay. What are the challenges? So sometimes it becomes difficult to find out what should be the initial point, what should be the seed point, and also this is a slow process, because as you know, from the seed point we have to analyze the pixels, this process is going to analyze the pixels with respect to seed point layer by layer, right? First, immediate neighbors are going to consider for the seed point, and then next neighbors and next neighbors, so on. So it is in some sense a time-consuming process. There is another variant of the region growing technique, which is called unseeded region growing technique. So in the seeded region growing, the earlier that we discussed was the seeded region growing, where we were deciding the seed point. But in the unseeded region growing technique, we don't have no explicit seed selection is necessary. In this case, we don't select the seed point, though this is based on based on a seed point, but explicitly we are not selecting any seed point. So here actually the seed can be generated automatically by the segmentation procedure. So we use some criteria to even generate the seed point. Right? So one of the criteria could be, like, for example, as we discussed in previous technique also, that suppose you know that something which you are going to segment is going to be very bright. So we can automatically say that whatever the highest intensity pixels are there in the image, they can be considered as seed point. So in this particular case, we are not specifically going and selecting the seed point based on some criteria, based on some automatic procedure. We are selecting the seed point. So it is actually similar to seeded region growing, except the choice of the seed points. right? There you are explicitly saying that this is a seed point, and then based on that whole procedure is carried out. In this case, we are not selecting the seed point. The process, the segmentation technique itself makes some uses some characteristics or some criteria to choose the seed point. Since we are going to, so there are some advantages if we have the unseeded region growing technique. Since we are going to, this technique itself is going to select the seed point, so then you can say that it is easy to use because we don't need to bother about the selection of the seed point. And it can actually readily incorporate high-level knowledge of the image composition through region threshold. As we saw in case of region growing, here also the same problem is there. This is relatively slower if you, let's say, compare with respect to thresholding based segmentation. This process is also slow process. Now this is another technique for region based segmentation. This is called region split and merge. So in the previous case, if you just compare the previous technique with this technique, in the previous case we had at the beginning we had a small region, and then we were growing to get enlarged region, and that way we were actually performing the segmentation. So initially in the previous case we had one point, and from that one point we have built up the segments. Now in this case the process is completely opposite. We have complete image. We are considering that complete image is one region, and then we divide the image into and we analyze actually the complete region of the image, and if we find that all the pixels of the image are not sharing the same characteristic, then we divide the image into segments, and we keep dividing the image into segments or in the regions till we find that we get a region where all the properties are same. So here, let us say this was the complete image given to us. Now we analyze the properties of all the pixels here, and then we found that all the pixels that are here in this region, let us call this complete region as R. That region doesn't, in that region, what all the pixels that we have, they don't share the same characteristic. So that means they cannot be grouped in one group. So what is the way ahead? In this case, then we divide into four parts. So we say that okay, this R is not sharing the complete property, so let us divide it into four parts. So now R has been divided into R1, R2, R3, and R4. Now for these segments we analyze their properties. So let's say we find that all the pixels which are falling in this region R1, they share the same property. So then we don't need to divide it in further. We can group all the pixels which are there in R1 into one segment. Similarly, let's say in R2 we found that it is also sharing all the pixels which are in R2 are sharing the same property. Then this can be they can be grouped into one segment. But let's say in this, and similarly is the case for R3, all the pixels have same characteristics, so they become one segment. But let's say in case of in R4, we find that all the pixels which are here in this region, they don't share the same characteristics. So in that case, we can actually divide it into further divide it into four parts and then analyze them further. So once we divide it into four parts, we have four regions. Now we analyze the pixels here, pixels here, pixels here, pixels here. If the pixels in these individual regions, if they satisfy or if they have the same characteristic, then we will not further divide that particular region. Otherwise, we will again divide it into parts, segments or regions, you can say. And how long we will keep dividing any region to further subregions till we find that whatever regions we are getting after this process of division, that particular those regions that we are getting after the division, they have these pixels which are having the similar properties, right? So for example, in after this division, you find that in R4, R41, R42, R43, and R44, the pixels that are there in these regions, they have the same property, then we will not further divide. But suppose we find that in R44 again, there are pixels which are not sharing the common characteristics, then we will again further divide this particular part, and we'll keep dividing this. And you can see that at the most, what will be the last stage. So at the end, maybe you have the region with one pixel. So if you get the region with one pixel, then you will not obviously You cannot go down, and then you have to stop there. So there are two parts here, two steps you can say. One is the splitting process, where given images or given image region is splitted into sub-regions, and this process we keep doing till we get all the regions where the pixels that fall in that particular region have the same characteristic. Now after this splitting process, there is a step called merging step, which is being carried out to finalize the segmentation, and this is actually required. So for example, you find that R3 and R41, they have the similar properties. They in the process of splitting, they could not join to each other, because when we divided the initial region into 4 regions, R41 actually fell this side and R3 was this side. But later you may find that these two regions are having the same kind of properties. So they need to be joined, because if they have the same property, they should belong to one segment. So that is why this process of merging actually analyzes the two neighboring regions, and if they share the same characteristic, then they are actually merged. And once this merging process is done, then we get the final segmentation output. So let's see the detailed step. So at the beginning, what we have to do, we have to split the initial image that is given into quadrants, as we saw in the previous slide, and we have to keep doing this process till we get a quadrant where all the pixels have similar characteristics. And where this is split into 4 disjoint quadrants, and is an Ri for which we have done this. If we just analyze the property of Ri, we will find that this property will be false, because since this property is false, that is why we are doing the splitting, right? As I said that if in this particular case, if you are analyzing the property of R4, you will find that property of R4 so the common property for this the pixels which are falling in region R4, they will not have this will not be true, because they will not have all similar properties. And since all the pixels which are in region 4, they do not have similar properties, we need to divide this R4 into further regions, right? So that's what exactly this step says. So whenever you are going to divide Ri into sub-regions, some disjoint quadrants, this is required if PRI is false, because if PRI is true, then there is no problem. Ri, all the pixels of Ri are one segment. Okay. Now in the process of merging, we analyze the adjacent regions, let's say Ri and Rj, and if we take the union of Ri and Rj, and we find that all the pixels that we are getting after this union, they have the same characteristics. That means this property, the common property that we are considering, that is true for region Ri union Rj, then they can be merged. And how long we have to perform this merging? We have to keep performing this merging till we get some option of merging. As soon as we find that there is no further merging possible, then we will stop. Okay. These are the outputs. So it actually compares the output of split and merge technique to the output of the thresholding based technique. So the last output that you see here is this output of the thresholding technique, and this output is actually for the split and merge technique. You find that in the case of thresholding, this particular part of the leaf, this part is not coming here. There is nothing with respect to that. But when you are using the split and merge technique, we are able to retain, we are able to identify that as a segment in the output. Okay. The reason we are not able to get in the case of thresholding, because the pixels which are actually making this part are very small pixels. So if you just plot the histogram of this, you will find that they will not have any representation. Sorry, these pixels will not have any representation in the histogram. So in the histogram, basically mainly you will see the pixels from this region and from this region. And these pixels will have a very minor presence. So that is why because they are very less in number, the threshold that is being decided will be based on these pixels and these pixels. So that is why in the output you are not able to see that part. Okay. This is the last technique that we are going to discuss. It is based on the watershed. It's called the watershed segmentation. So now let us first try to understand what we exactly mean by watershed, and then we'll follow. We will discuss the related things. So if you just consider this natural image, you find that when and let's say when the rain happens, the water get accumulated at some places on the land. Okay, so you can see here that if let's say the water drop falls here, where will it get accumulated? It will actually come to this side and it will get accumulated here. Similarly, if you see, if there is a water drop that falls here, it will come and get accumulated here. Similarly, if there is a water drop, let's say, falls here, then it will get accumulated here. If it, let's say, falls this side, maybe, then it goes and accumulates here, right? So in this whole region, we'll see that there are some points for which if the water drop falls there, the water will be actually accumulated to a common point, right? As you see here, all the, you can say maybe like this, that all the points here on this land, let's say inside this region, wherever I mean this water drop falls anywhere in this particular region, the water will be actually accumulated at this in this region only here, right? Similarly, if you consider this part, you will find that there is some region here for which if you consider the fall of water drop, then finally the water is going to come and accumulate here. Okay, so in a particular region or the area of land where you see that when the water falls, it drains to a particular point along a stream, then all those or that particular area or all the points in that particular area, they actually make a watershed. Okay, so for example, you can say that in this particular image, this is one watershed. Okay, similarly, this is another watershed. You have another third watershed here, like this. This is one watershed here. So I'm just highlighting some, but with respect to any point, actually, you can define a watershed, because if water drop falls on this land, it will go and accumulate at some place. So based on that accumulation, you can group the points which are actually from where the points, if the water falls accumulates to a common point, those points can be actually grouped and considered as one watershed. So here I have just marked few watershed, but with respect to any point that you have here, you can make a watershed. Okay, more precisely you can see that thing here. So for example, in this image, this is again a terrain, and this arrow is basically showing that anything which is falling inside this region, I mean, like if the water falls anywhere inside this region, it actually gets and accumulates here. Similarly, if the water, let's say, falling in this region, water drops, it falls in this region, it actually comes and accumulates here. Similarly, there are some points for which the accumulation happens here, and so on. So this is called these points are the area of land that drains to a particular point along a stream. This area is called the watershed. Now, if you see again, let's say come here. So in these watershed, you find that, let's say, you are moving in this watershed, you are moving from this direction to this direction. So as you move like this, you will find that this point also drains to this side, this point also drains to this side, similarly this point also drains to this side. But you will find there will be one place here at which it can actually drain to either side, right? I mean, like something like the situation here is exactly similar both the side. It can go this side also, it can go this side also. So around any watershed you can find such points where if the water drop falls, it can go to one side, go to the watershed of the one side, or it can go to the other side. So such points, if you join them, they are actually called the watershed line. So all the blue lines that you see here, actually, they are actually showing the watershed lines. So in this process of segmentation, which is based on watershed, we'll see that our objective will be to find out these watershed lines, because I mean, as you see from here in this image, anything which is inside this watershed line, they have some kind of similar, you can say in some way similar properties. In terms of watershed, you can say that they all drain to a common point. With respect to image also, we'll see. So since all the pixels which are going to fall within this, let's say, watershed line, they are going to share the common characteristics, so they can be called one segment. So our objective in case of watershed segmentation is to find out these watershed lines, and if we are able to detect those lines, then anything which is inside those lines will be considered one segment. Okay. So now how are we? So here we are able to define watershed because there is a difference in the height with in the points that we have on this terrain. Right? There are some points which are deep. There are some points which are, let's say, at some higher altitude, and so on. So how are we going to have similar thing in case of image? So in image also, actually we can consider our 2D grayscale images as a kind of a 3D terrain. If whatever intensity we have for the pixels, that intensity we consider that is kind of our Z. Okay. So if you let's say this is our grayscale image, and then every intensity is like projected into Z, and that Z defines the height of that pixel. So you will see that the image will be like this. This image is little rotated so that you can visualize the 3D. But if this was the image in 2D, exactly at the same XY, you have projected the point in the Z direction. Okay. This is a point cloud representation where every pixel here is represented in terms of points, but there are also methods where you can actually triangulate this and have a better visualization. These two are representing actually the same thing. This is also a 3D representation of this 2D image, and this is also 3D representation of the 2D image. So when we are using the watershed segmentation, this grayscale value, or the gray value that we have with respect to a pixel, that is going to serve as the depth. Or if you compare this with the natural watershed, whatever height a particular point had in the natural watershed, that height is going to be represented here with the help of the gray values. Okay. So when we are visualizing our 2D images, we can say that we can have a visualization in terms of 3D topographic view. Whatever we had actually here, you can consider this or this as a 3D topographic view. This is another example. Here you have a grayscale image, and when you are projecting all the images, sorry, all the pixels, considering their intensity value at depth, you get this kind of representation. Okay, so this is a 2D image, you can say, and this is in some sense you can say the visualization in 3D. Okay. So if you analyze these watershed regions, you can actually find out that there are 3 types of points in the watershed region. One is the regional minimum. That means the place where this all water actually in a particular watershed, the point where this whole water accumulates, that is a minima. In terms of height, you can say that will have the minimum height. That is why the water is coming and accumulating there. And so you will have a minima. You will have watershed points, that is also called the catchment basin. Catchment basin or watershed points, these are the points where if a water drop falls, it accumulates to a common point. Right? So one is the regional minimum, then another is the watershed, and third is these watershed lines are the dividing lines. So let us say if you consider this particular region, so whatever I am drawing is actually the watershed line. Right? You can say this is watershed line, and all the pixels which are falling in this red region that I have created, they all are the watershed points, or you can say they define the watershed. And the point, let's say, marked by these arrows here, they are the points where the water is accumulating, so they are called the point with regional minimum. We are saying regional minimum because the minima that is there in one watershed may be different from the other watershed. For example, in this in the 2D, this is a 2D cross section of the watershed. You see that in this watershed the minima is here, but in this watershed the minima is here. So minima may be different for different watersheds. So that is why we are saying that this is regional minimum. This is not the global minimum. This is the regional minimum. Okay. Now let us understand how we are going to use this technique for segmentation. So our 2D images, you can consider them like a, let's say this is a kind of ice cube tray where, let's say in the phrase you make the ice cubes. So our 3D images, 2D images, if you project their intensity to 3D in the z-axis, then you can visualize our 2D images like this, where you have some cavities and there are some pixels which are raised high and so on. So in this, if let's say you have the representation of our 2D image like this, then in this case, in this representation, our objective, if you want to segment this image, is to find out these some lines here around this. I mean, inside this image, we want to find out some lines here, which are the watershed lines, right? This is the objective. Now, how we can find out these watershed lines? And as we know that in watershed line, if you, I mean, whatever pixels or whatever the points we have inside this region, if water falls, it will actually accumulate at same place. So similar thing you see here. So if anywhere, if the water falls, it is going to accumulate here, right? Similarly, it is going to accumulate here. It is going to accumulate here in this watershed. It is going to accumulate in this watershed. So for these watershed, how to find out these common lines, okay, or these dividing lines? So the procedure is simple. You can just visualize as if there is a hole in these I mean in these segments in this image, or I mean you can just consider this a physical tray at this moment. So in this physical tray, you can assume that there are holes in these cavities. Now and you are filling, let's say, the water from the bottom. So when you fill the water from the bottom through these holes, you'll find that the water level will raise in these regions, and slowly when the water raises, you will find a case when this water will merge with this water, or this will start merging with the neighboring water from the neighboring segment. So we have to just find out those lines where the water from this body starts merging with this body, because that is the place where you have the segmentation lines or the watershed lines. Okay. So the idea here is follows. So you can suppose that there is a hole below, a hole in this segments in the each region that you are considering here in this image. We can consider there is a hole there, and then this body is flooded from the bottom, and we can say that as soon as the water, when you are raising the water level in these bodies, as soon as the water starts merging, let us say to stop that merging, we create a dam there. So that dam actually will represent the watershed line. So let's say to merge the water from this body to this body, we are creating a dam here. So that dam actually avoids or prevents merging of water from here to here, and that dam will be nothing but the watershed lines. Okay. So our objective is to compute these watershed lines, and or in other way you can say that the points where we are going to create this dam. Okay. So in terms of images, you can visualize this. I mean, I've just shown you the physical, I mean, interpretation of this technique based on these physical objects. But in terms of images, you can visualize it as follows. So let us say you take, for the simplicity, I'm just considering a 1D case here, but the same is applicable for the 2D. Let us say in your image, you take the 1D cross section of the intensity in your image. Right? This means you have, let's say, image like this, and in this image you have just taken the intensities which are following, like let's say in this particular row. So all those intensities are plotted here. So this is distance versus brightness. And distance is nothing but the pixels. So you have the first pixel here, and then let's say this is a 100 cross 100 image, then the 100th pixel is actually falling here. Now in this case, here you are, let's say, these are the minima that you have, and let's say you create a hole here or hole here and hole here, and then you fill the water from the bottom. So you find that when the water is raising, the first dam will be, if you just come here and see, when the water is raising, you have to make the first dam here to stop merging of this water to this water. So that will be one. So this will be the first line that we will be creating. Then similarly, when you again, if you keep rising the level of the water, then you'll find that this water will actually keep start merging with this water. So to stop this merging, we'll create a dam here. So these are the 2 points actually which will create the segmentation line or the watershed line, are the points where we are going to create the dam to stop this merging. Okay. So let us see how we are going to implement this. We are saying this water here, but what exactly we do when we are going to implement this in case of images. So please remember that whatever depth I am showing here, this depth is going to be represented with the help of intensities. So what is the, if you consider that the 255 is the lowest depth, what is the highest depth you can have? If 255 is the lowest point in this representation, then what will be the point with the highest height? The point where you have the value 0, right? Because this intensity or the gray value or gray scale is going to represent the height here. So how are we going to start? Here I said that we are creating some holes, and then from holes the water is being filled. But those holes are the, if you see here, those holes are the points where we are going to create hole here. They are the point where which are at the lowest level in this profile. So how will we select those points? So that we can analyze and do that selection as follows. So we can start with all the pixels with the lowest possible value. So in your image, let's say your gray value ranges from 0 to 255. So considering let us say 0 is the lowest level, or as we said here 255 we are considering the lowest level. So we can start from the 255, right? Or we can start from the 0, whatever we are considering as low. So all the pixels which are having that low that we are going to consider, all those possible pixels are going to serve as the point from where this water is going to be filled in the different segments here. Okay. So we are going to start with the lowest possible value. That lowest possible value, again, if this is the profile here. So what is the lowest possible value here? So this is one lowest possible value. From here we are going to start, and we can theoretically assume that the water is being filled. What equivalent to this we are going to do here, we are going to see here. So the first step is to start with all the pixels which are having the lowest possible value, and this lowest possible value is in terms of intensity. Right? We have the choice of making 255 as low or 0 as low, whatever we want to use. And these actually points form the basis for the initial watershed. So these are the basis points, or these are the initial points from where we are going to consider that the water is going to fill in the body in those segments. Okay, then after that what we are going to do? Then after this, for each intensity level K, we are going to start for each intensity level K that we have in the image. For each pixel intensity K, if adjacent to exactly one existing region, this is, we are actually talking with respect to one pixel, you will find that adjacent to this particular pixel, if it is adjacent to exactly one existing region, then we have to add this pixel or these pixels, if you have multiple pixels in consideration, into the same region. Okay, what exactly here we mean by this? So let us say we have this is the lowest point we have considered here, right? And this has, let's say, the intensity value, let us say 200. Okay, now from 200, since we are going towards 0, so when we are saying that we are increasing the water level, this basically means that we are increasing the intensity level. So when this was 200, next it will be 199, and then So this k, I'm telling the value of possible k value of k. You have started from 200, but now this k is going to take 199, 198, 197, and so on. But when you get a value, let us say, which is equivalent to this, like let's say some value here, let's say 150. Now 150, you see, before 150 everything was in this particular region, but as soon as you consider this value 150, you will find that this is actually adjacent to two regions. One region which is being formed from considering this particular pixel, and another region which is being considered from which is being formed by considering the water leakage, let's say, at this point. So when you find a point here which is adjacent to actually two regions, that is actually going to define the splitting, that is going to define the boundary. So when you are raising the water level, or when you are increasing your intensity, for every intensity k that you are considering, if the new pixel that you have considered, it is adjacent to only one region, then this will be the part of that region to which it is adjacent. But if you find that it is adjacent to more than one existing region, then that is actually a case of boundary pixel, and that point need to be marked there. And once you mark such all such points, then you will see that those points are going to form the watershed lines, or the lines which are going to define the segmentation. Okay, and this is an iterative process. As I said, we are starting from one lowest point. Okay, so let's just say here, yeah. So for example, if we have considered this as the lowest point here. Okay, now when we are considering this as the lowest point, we will be forming this one. But in the process, when we are moving from here to here, we will encounter this particular point here, which is the lowest, right? So when you find that there is a pixel that you encounter for a particular k which is not adjacent to any region, then that will start forming a new region, as you see here. As you see the third point here. So first point actually says that if a particular pixel is adjacent to only one region, then it will be part of that region. It will become part of that region. Second point says that if the pixel is adjacent to two regions, then it will be part of, it will be actually a case for the boundary. And if it is satisfying neither of these cases, then it will start a new region. Okay, so let me just come back to this example again, and let me explain this here. So at the beginning, you will start with this pixel, right? And all the pixels which you have in this region here, they will be actually part of only one region, so they will keep accumulating with this region, right? Similarly, in this process, after certain k's, you will find that you will encounter a k which is here. Now this k is very far from this region, so this particular pixel for that selected k, it will not be part of any region, or it will not be adjacent to actually, it will not be, I mean, first it will not be adjacent to one region, and also it will not be adjacent to two regions, obviously, and that is why this will start forming a new region. So if you see these steps, this second step that you have here, this second step in this process is going to occur when the formation of this water level when keep rising in this segment, and when it rises in this segment, and after certain iteration you find a k where that k is actually, I mean, pixel with respect to that k is adjacent to two regions. Okay, so with respect to this algorithm, this particular pixel, you can say that is coming because of the first step, but when you are adding this particular step, this is coming because in fact both these points, this point and this point, they both are coming because of the third step that we have. We are starting a new region, but now when you are accumulating the points in this region, they all are coming because of the first point, or the first rule. And this particular point, when you are marking here, this is being marked because of the second rule, because this particular point is adjacent to two regions. Okay, so let's see this example here. This was the original image which we want to segment, and again this is the original image in terms of 2D image, and this is in terms of the 3D. This is a topographic view of the same image. Right? Image is given in this format, but just for the visualization we are thinking that it is like this. Now here you see that the water level is rising. That means from the lowest level we have started in these images, and we are increasing the water level here. When you are saying that water level has increased from, let's say, one step to the another step, that means first you considered the pixels with intensity, let's say 200, then now you are considering the pixels with intensity, let's say 199 and then 197, if we assume that the lowest is 255. Okay, so all the pixels which are actually being shown here with the same color, you can say that they have the same, they are representing the water. So all the pixels, like, here you see that they are having the same color. So that means all the pixels which were below these pixels, their intensity have been raised to this common value. So now if you keep considering the increment in the intensity in the pixels that are there in the image, slowly and slowly you will find that these areas will increase. So let's say initially only these pixels will have this region, but when you say that now intensity is going to raise to further one, to the next level of the intensity. Let us say these pixels are representing, let's say 255, 225 value. So the next pixels that are going to be here in the surrounding area, they are going to have very similar kind of intensity. Might be the intensity just one more than the intensity that you had for these pixels. Because why this? Because that you see from the nature of this topographic view. As you are moving, let's say from here to here, this side the intensity is increasing. So initially you had pixels, only these many pixels included in this region, but as you increase your intensity level, then as soon as you make your intensity level to the next level, then more pixels will come and join this region. And this will keep happening. As you see here, these regions are growing slowly and slowly, and ultimately you find a case where these two regions are approaching to each other and getting merged. So in that case you will find that these are the pixels where this is adjacent to this region also and this region also. So that is why the boundary has been placed there. And if you just do that for all the pixels that are here in the image, which are forming these watershed lines, you will get image like this. And the segment in these images, in this image, our segments are going to be formed based on these boundaries. So we'll have one segment here, another segment here, another segment here, another segment having this all area, and so on. Okay. What are the applications or what are the places where this watershed segmentation can be applied? So normally it is applied where we have nearly uniform blob-like objects. For example, here. So as you see here, this is one blob, this is another blob, and we want to actually segment these blobs. So in such cases, this algorithm can be useful. And normally, when we are using the watershed algorithm, in place of using the intensities directly, we consider the image gradient and then we perform the watershed algorithm on that. And that is exactly being done here. This was the original image, and then from that we have computed the gradient image, and then on gradient image watershed segmentation has been performed. And based on the watershed lines, this is the final outcome. These are the watershed lines actually obtained on the gradient image, and then when these lines are placed on the original image, we get this final segmentation. So the watershed line here and here, they are same. Only in the first image here, they are actually superimposed on the gradient image, and in the next here, they are superimposed on the original image. Okay. In edge-based segmentation, our objective is to actually compute the edges in the image, and then we perform edge linking to get a closed boundary, and that way a segment is defined. So for example, here if you want to do segmentation, first in this image the edge detection is performed, and then we trace the edges and then try to link two edges so that we get a closed boundary, and that those closed boundaries actually denote the boundary for this segment. So you see here in these images, Both the images are showing the final segmentation output for edge-based segmentation. And here the procedure is simple. You have to take the image, you have to compute the edges, and then you have to link those edges to form a closed boundary. And based on those closed boundaries, we have to define the regions. For example, here we get a closed boundary, so this defines one region. Similarly, this is another closed boundary, so this defines another region. This is another closed boundary, so this defines another region. Now, if you compare this slide with the previous slide, the slide that we saw for the region-based segmentation, there we were highlighting the region. So all the pixels which were in one region, they were actually shaded with one color. But here we are not doing that. We are highlighting the edges. So all the pixels which are actually forming the boundary, we are detecting them and we are highlighting them. So here we are not analyzing the similarity of the pixels. We are analyzing the dissimilarity, and based on that we are doing the segmentation. Normally it is seen that if we have the image, if we have the noise in the images, then in that case region-based segmentation is better compared to the edge-based segmentation. So that means edge-based segmentation is only is applicable. It can give good results if we have images which are free of noise. If we have the noisy case, then we should go for the region-based segmentation. That means the technique we discussed earlier. This technique may not yield good results. Okay. So with this, let us conclude today's class.